Good morning. Good morning. Okay. So now you are able to see my screen. So what was the things that was taught to you in the last class? Where did we leave? Yes, can anybody say? Where did we leave in the last class?
Test your understanding 5.3.
This call is now being recorded.
Your understanding 5.3.
3.
5.3. So that was over, I think. And the assignment exercises, have you taken the screenshot? Of the assignment exercises? What about the assignment exercises?
5.3 is not over.
Oh, 5.3 is not over. That those different situations where the frictional force
Only
is
question
zero.
is written.
Okay, okay. We'll start with that. Just wait. Just wait. Okay, so this was the test your understanding. And consider a box that is placed on different surfaces. In which situations is there no friction force acting on the box? In which situation is there a static friction force acting on the box? And which situation is there a kinetic friction force on the box? The box is at rest on a rough horizontal surface. This is one situation. The box is at rest on a rough tilted surface. First we will see what are the forces acting on the box when it is rest on a rough horizontal surface. Okay, so the box is, this is the horizontal rough surface and the box is placed here. So the forces acting is the weight vertically downwards and the normal force upward. Because there is no motion, it is at rest. So the net forces acting on the box is 0. And because the applied force is also 0, because force of static friction is a self-adjusting force, so force of friction is 0. I have written this F as force of friction. So force of friction is 0. Now I will go to another example. This is an inclined plane. The same box is placed here now. Okay. And we have to see whether the frictional force is 0 or there is force of static friction or there is force of kinetic friction. So again, I will show the forces acting on the box. One is its weight acting vertically downwards and another is the normal force, isn't it? And I have told you very categorically that when you are doing the banking of a car, then you have to take horizontal surfaces, this horizontal and vertical axis. But when you are doing this type of inclined problem, it is always better to take axis parallel to your inclined surface, isn't it? And perpendicular to the inclined surface. So this is my N and this is my W. So in this case, I am going to resolve W into two components. In the earlier case, in the banking of the curve, I was resolving N into two components. So those two things you have to be careful. So when I will resolve this W into two components, one will be W cos theta, because
So
this
can you
angle.
repeat?
What happened?
So can you repeat?
Okay. Yes. You have seen that while I was teaching you banking of the curve, normally what happens, road inner edge, and if this is the outer edge, then compared to the inner edge, I elevate this outer edge by some height, isn't it? By some height, and or by some angle. This angle is called beta, angle of banking. banking, isn't it? So this is your outer edge. You see, this is actually your outer edge. This has been elevated compared to the inner edge, because you are not going to find out the force parallel to this inclined axis, because you are interested to find out the centripetal force along the radius towards the center. So your radius, your circle is this one, which is in the horizontal plane, not in the elevated one. So you have to find out the force along this radius towards the center. So there is no point taking these as the axis. Okay, you should not take this as axis. So if they are and vertical axis, and there I showed my force. So I showed my W like this, but my normal must be perpendicular to the inclined surface. So I show my N like this. So in the banking of the curve, because I have shown my N like this, so I have to resolve my N into two components. One is N cos beta and the other is N sin beta. So this was my N sin beta and this was my N cos beta, isn't it? So here in the banking of the curve problem, N cos beta was balanced by W and N sin beta was giving you the required centripetal force, because you need the centripetal force not along the inclined plane but along the horizontal plane. But here, though both of them look like inclined planes, but
So you are not audible.
along this, it is advantageous to take the inclined the axis parallel to the inclined plane. That is the only difference. I hope you have understood, isn't it? Have you understood?
Sir, in between, sir, your voice was not audible, sir.
Now am I audible?
Yes, sir.
Okay. So this is how, just to distinguish, because here we commit lot of mistakes, misconceptions are there, because if you resolve, where actually if you are going to resolve N here, then you will be in problem. Similarly, if you are going to resolve W or here, then you will be in problem. Actually, you will not be in problem, but the problem will look very complicated. Again, you have to come to the here. If you take horizontal vertical axis, then you have to find out a component parallel to the inclined plane. And if you choose inclined axis in the banking problem, then you have to find out the force along the horizontal. So why you will unnecessarily make the problem complicated by choosing your axis differently. So always choose the axis in such a way that will be advantageous for you. So when I will resolve these two things, this N into 2, this W into two components, I will get one is W cos theta, which will balance by the normal force, and there is an unbalanced force which is W sin theta. So this W sin theta is pulling the box downwards. So your applied force is W sin theta. So what will be your force of static friction? Can anybody say? Now your applied force is W sin theta. So what should be the frictional force, force of static friction?
Mu Sn.
It was? Yes?
Mu Sn. Mu Sn.
No, no. Why it will not be mu Sn? Because mu Sn is Fs maximum. That is the maximum static friction. Yes, actually all of you should answer. Once you answer, then misconceptions will be clarified. Mu Sn is the highest amount of, or the maximum amount of force of static friction. That is the highest point. Fs maximum, isn't it? Fs maximum. But your body is at rest. That means you have not yet reached the force of maximum static friction. You have not yet reached mu Sn, because your body is at rest. How do you know? If your body is at rest, that means still you are in the region of force of static friction. But if your body starts moving, then you have reached this condition. And if the body is already moving, then now Fk is acting, force of kinetic friction is acting. So this is how you have to understand. So your W sin theta is equal, because force because force of static friction is a self-adjusting force. So Fs will be equal to W sine theta, and Fs is not equal to mu Sn. That you must understand. Fs maximum is equal to mu Sn. Okay, so Fs has not yet reached its maximum value. So Fs is equal to W sine theta. So what are the net forces acting on the body? Both along the vertical direction and the horizontal direction, net force is equal to 0. So the body is at rest. So what you will see, where we are going to conclude, yes, in the inclined plane problem, there is force of static friction. Here, force of static friction or frictional force is 0, but here, static frictional force is present. Okay, now we'll go to the third part of the problem. The box is on the rough surfaced flat bed of a truck. The truck is moving at a constant velocity on a straight level road, and the box remains in the same place in the middle of the truck bed. Box is on the rough surfaced flat bed of a truck. So the box is placed on behind of the truck. That means on its flat bed, but that is also friction is there because it is a rough surface. But the truck is moving at a constant velocity on a straight road. So the direction is also fixed, the speed is also fixed. And the box remains in the same place, in the middle of the truck bed. The box is also not moving, though the truck is moving. Okay, so how we are going to find out this problem? So let us say that this is the truck's dala or the back side of the carriage. Okay, the box, this is the rough surface, and the box is at the middle. Okay, and the truck is moving with constant velocity. So V is equal to constant. So both the direction and magnitude is equal to constant, because constant vector means the vector has fixed direction and fixed magnitude. What are the forces acting on the box? Weight vertically downwards, and the normal force vertically upwards. And there is no force because the box is at rest. Now, can you say what are the forces acting on the box? Is frictional force acting on the box?
No, sir.
Is there Fs? Is there Fk? Is there Fs? Is there or Fk?
Kinetic will be, but static force won't be acting.
Yes, what? Yes, please
So
tell.
kinetic will be there, but static force won't be there, sir.
Kinetic force will be there.
Yes, sir.
No. Why kinetic force will be there? Actually, that is not kinetic force, force of kinetic friction.
Yes, sir. Yes,
So
sir.
according to you, there should be force of kinetic friction. But why? Why? Because you see, there is very important thing you must understand from two things. I have told you repeatedly that a state of constant velocity and state of rest are identical. There is no difference at all. So in the first problem, your box was at the rough horizontal surface. Similarly, here the box will not know whether it is on the rough horizontal surface or it is on the flat bed of a truck which is moving with a constant velocity. Because a constant velocity and state of rest are exactly identical. Just like a state of rest, because when the box is moving with in uniform, and that's why you see, that's why actually that's why the box is at rest. The box is not the box has not displaced from its main position, or the middle of the truck. Wherever the box was there, the box continues to lie there. That means definitely net forces acting on the box is 0. So when the net forces acting on the box is 0, there is no applied force, nothing else. So the frictional force is 0. Frictional force is 0. So no questions of any kinetic friction. Kinetic friction arises when there is motion. So the truck is moving, but the box is not moving. So why there will be kinetic friction in case of the box? Because that is what he is asking. He is not asking about the
Okay, sir. Okay, sir.
whether force of kinetic friction isn't understood.
Yes, sir.
Okay. Just wait. Now we'll go to the fourth part. Just first let me erase it. The box is on the rough surface flat bed of a trough. Now the trough is speeding up. Okay. Now what is happening, I will tell you. Now here this trough. Just wait. Just wait. Okay, am I audible now?
Yes, sir.
Yes. Okay. So now the box is there, same at the middle position, but now your torque is not moving with uniform velocity. Now acceleration is present. Okay, A is speeding up. That means on the torque. Okay, because there is force on the torque. And what is happening to the box? Let us see. And the box remains in the same place in the middle of the torque bed, but the box is not moving. Box is at the same place, but now there is a force acting on the torque, otherwise where from this acceleration is coming. So the force is also acting on the box. Okay, there is a applied force like this. So now there are three forces. One, the weight, another the normal force, and then the applied force. Okay, but the box is not moving from its position. So the box is at rest. That means the box is in equilibrium. So there must be another force acting in the opposite direction like this. So this force must be the force of static friction. Okay. Again, the force of static friction has not reached its maximum value. Otherwise, the box would have started moving. So here Fs is present. Okay, Fs is not absent. Fs is present. Because unless Fs is present, the applied force will act on the box and the box will start moving with an acceleration. That is not happening because the box is in equilibrium. So all the forces are balanced both in the x direction and in the y direction. Then we'll come to the final part. The box is on the rough surface flat bed of a trough. Now the trough is climbing a hill and the box is sliding towards the back of the trough. Okay. Now the trough is climbing. Okay, so this is how you see the trough is climbing like this in this direction, and the box is moving, sliding in the backward direction like this. The box is sliding. Okay, now what is happening? Let us see. Now you see one force, the weight is acting like this. Normal force will act like this. Weight will be resolved into two components. One component like this, another component like this. Now this is wiggled out. Now this W cos theta will balance the normal force. This is W cos theta, and this is your normal force. They will be balanced. So W sin theta will try to pull the box. But W sin theta must have reached, because the box is now moving. So W sin theta must have reached the value of maximum force of static friction, or that mu Sn. And that's why there are two things which the problem is not telling, whether the box is sliding with uniform velocity or with an acceleration, that is not clear. If it is sliding with an acceleration, then W sin theta is greater than Fk, because Fk is acting, because now the box is moving, so force of kinetic friction is present. So if W sin theta exceeds Fk, then the box will move with constant acceleration. But if W sin theta is equal to Fk, the box will move with constant velocity. Isn't it? Yes, constant velocity. Because it is not interested in those kind of details. Only the question is interested to know whether what type of frictional force is acting. Because the box is moving, so you have to say that force of kinetic friction is acting. And in all the four situations, the box was not moving. So in some cases, there was frictional forces, which is force of static friction. And in some other cases, there was no friction at all, no frictional force. Okay, that is how you have to shade. Now, I will give you the assignment exercises. You will take a screenshot and then we will go to, I will present a summary of whatever we have learned in chapter 5. Then we will go to chapter 6. Okay. So, the assignment exercises. So now I have, so the first bit is no frictional force. Second bit, frictional force of static friction. Third bit, no frictional force. Fourth bit, force of static friction. And fifth bit, force of kinetic friction. Okay. So these are the, first you take this assignment, the screenshot of this question. 5.10. Take a screenshot and tell me that you have taken. Then I will go to the next page. Have you taken?
Yes, sir.
Okay. This is 5.10. Then you take another two. 5.25 and 5.28. Have you taken?
Yes, sir.
Okay. Then now we'll go to the summary part of chapter 5, whatever I have told you. So this is the so there are 4 topics in chapter 5. Using Newton's first law, particles in equilibrium, 5.1. Using Newton's second law, apparent weight and weightlessness, 5.2. Frictional forces, 5.3. Dynamics of circular motion, 5.4. In 5.1, there is test your understanding 5.1. 5.1 is that traffic light balanced by 2 ropes, which are placed 45 degree at 45 degree angle, and find out the tension with respect to weight. And tension T is equal to W by root 2, that we have found out. And there are examples. 5.1, a gymnast is hanging from a rope of negligible mass, and you have to find out the tension at the bottom and at the top. Then, though there is no 5.2, we have worked out 5.2. The same gymnast of 50 kg mass is hanging now from a rope of weight 120 Newton. Once the rope has a weight, now the tension will be different. The tension will be minimum at the lowest point of the rope, and it will be maximum at the topmost point of the rope, isn't it? Then we learned about Newton's second law. In the 5.8 example, we worked out that elevator problem and we find out the tension. The elevator was moving with 10 meters per second downwards, and it came to a rest within 25 meters. From there, we found out its acceleration to be 2 meters per second square upwards. And from there, we calculate the tension in the elevator cable. Then there is no example 5.9, I have worked that example 5.9 for you so that you can understand apparent weight and weightlessness. From that, actually, we derived a equation for the normal force. You must have understood that is a beautiful equation. N is equal to, isn't it? N is equal to M into G plus AY, isn't it? So the presence of this AY is actually creating the sense of apparent weight and weightlessness. When this AY in the problem was 2 meters per second square, because for the same lady whose mass was 50 kg, his true weight is 490 Newton, isn't it? But when she is writing that elevator in the question, her weight will become extra 100 Newton, and she, because as AY is equal to 2 meter per second square, that we have found out. If the acceleration will be minus 2 meter per second square, the ladies will have a weight of 390 Newton. So these variations in weights are known as apparent variations or apparent weight, because once all these effects are due to the lady is being in the elevator. Once the lady will come out of the elevator, this perception or this sensation of overweight or underweight will disappear, and that's why this is called apparent. Now when AY is equal to minus 9.8 meter per second square, N is equal to 0, and the lady will feel a state of weightlessness, as if she has all her weight has gone, but actually the weight is still there. That means the earth is pulling, but the sensation of weight will not be there. That's why that is called apparent weightlessness. Okay, that also we have discussed in example 5.9. So we have discussed 5.1, 5.2, 5.8, 5.9. Then in the frictional forces, this test your understanding 5.3, just now we have worked out. 5.13 is that box of 500 Newton, which was pulled with a 230 Newton force to break it loose or to start motion, because that is the force of maximum static friction. But in order to maintain the box motion with the constant velocity, 200 Newton force is enough. So 200 Newton is mu Kn. Mu Sn is 230 Newton, N is 500 Newton, mu Kn is 200 Newton, and you have to find out mu S and mu N. And this is an important question for examination. Normally, every year this question is being asked. So mu S is equal to 0.46 and mu K will be 0.40, and these are dimensionless constant, no units. Then we go to the toboggan problems. 5.16 is there in the example only in the lesson plan, but I have worked it out for you 5.13 and 5.17. 5.13 5.10. 5.10, when there is no friction, so the toboggan will move with acceleration. 5.16, there is friction, but the toboggan is moving with constant velocity. And 5.16, there is friction and the toboggan is moving with acceleration. So that is also is a very interesting equation. That equation is AX is equal to Z. If you remember, G into sin alpha minus mu K cos alpha. Sin alpha minus mu K cos alpha. Alpha is the angle of the inclination. Mu K cos alpha. Mu K is the coefficient of kinetic friction. So when mu K is equal to 0, the second term is 0 and AX is equal to G sin alpha, you go back to example 5.10. When AX is equal to 0, G sin alpha is equal to mu K G cos alpha, G cancelled, sin alpha is equal to mu K cos alpha, or tan alpha is equal to mu K, or alpha is equal to tan inverse mu K, and you go to example 5.16, isn't it? And when alpha is equal to 0, you are in a horizontal plane, then this first part will be 0 and AX is equal to minus mu Kg, isn't it? And when alpha is equal to 90 degree, then the second part will be 0 and you have AX is equal to G. So whether the object is in a frictional surface or no frictional surface, when the angle is 90 degree, there is no contact between the body and the surface and the body will have a free fall. So all these interesting consequences have been discussed. Okay. Now we come to dynamics of circular motion. In the dynamics of circular motion, test your understanding 5.4, we have already worked out a satellite moving with a smaller radius of orbit and a satellite moving with a larger radius of orbit. And we have to find out how the gravitational force of attraction behaves with increase in distance. And we have concluded that once the the gravitational force of attraction will decrease once the distance increases, because here the speed is more and here the radius is less. Here the speed is less and the radius is more, okay, isn't it? And the centripetal acceleration is inversely proportional to radius and directly proportional to square of the speed. So naturally, here the centripetal acceleration is more, centripetal force is more. So more force here, less force here, less r here, more r here. So the force is less when the r is more. The force is more when the r is less. So because the centripetal force is being provided by the mutual force of attraction between the earth and the satellite, that's why we will conclude that the force of gravitation decreases with increase in r. Then we did 5.21. 5.21 is unbanked curve. The somebody is driving a car in a flat road and taking a turn, and with what maximum speed it can take a turn, and that we have found out in presence of friction, of course. But if there is no friction, then what will happen? Then we have to bank the curve unless the outer edge is elevated compared to the inner edge, and if there is no friction, you cannot take a turn. But once you have banked the curve, then it will be easier for you to take a turn, and we have found out the angle of banking. Then in 5.23, we discussed about the motion of uniform motion along a vertical circle, and we showed that the normal force or the force exerted by the seat on the passenger will be more at the bottom and it will be less at the top. So and now I have also given you 3 assignment exercises. Hope you will do all these things in your home and try to read as little as possible, so that the understanding will be clear. The more you read and more confused you are, then everything will be spoiled, isn't it? So now we'll go to chapter 6. So let me, because we have got lot of time, so I think we should go to chapter 6. Chapter 6 is a small chapter. It is work and kinetic energy. So the name of the work and kinetic energy. Okay, chapter 6 is work and kinetic energy. Work and kinetic energy. There are 4 topics, very small topics. What is work? 6.1. Then kinetic energy, work energy, kinetic energy and the work energy theorem. Kinetic energy and the work energy theorem. And the work energy, let me put a hyphen, work energy theorem. That is 6.2. And in 6.3, the same work energy theorem, we'll find it out for varying forces, work and energy with varying forces. And finally, power. All are very small topics. Then there are 2 tests your understanding, 6.1 and 6.2. 3 examples, 6.2, 6.3, 6.10, and 3 assignment exercises. So what is work? Now we'll go to the introductory part. Okay. So normally what is happening, work. So for work, we'll use the symbol capital W. Okay, because small w we are using for weight. And you know, work is actually done by a force. force must be there to do work. And how it does work? It does work by displacing the body. Displacement is a vector quantity, force is a vector quantity, but work is a scalar quantity. So that must be, work must be the dot product of force and displacement, or that is equal to Fs cos theta. Fs cos theta. What is F cos theta? F cos theta is the parallel component of force. So who is actually responsible for doing what? The parallel component, not the perpendicular component. Because F cos theta into S, F cos theta is parallel component of force. So I have written F parallel into S. So the perpendicular component is a silent spectator. It doesn't have any role in doing work. It does other things, but it doesn't do any work. That you must understand. Okay, for a straight line motion, theta is equal to 0 degree, and if there is a constant force and the force and the displacement are along the same direction, then W is equal to, very simple, because now F is equal to F cos theta. So you can write W is equal to Fs, force into displacement. But your life is not always that easy, because if the force is variable, you cannot write work as F into S. But that we will look at topic 3, work done by varying forces. From this W is equal to Fs, we can find out the unit of W, because unit of force is Newton and unit of displacement is meter. So Newton into meter, this dot means into. So Newton into meter is joule, and joule is capital J. So 1 joule is equal to 1 Newton into meter. So you must not write, this is correct. Either if you write, you can write Joule, joule. This is correct. But don't write JUL, lot of JOULE. This is correct. But this is wrong. This JOULE. Okay, this is the name of the scientist. So don't write the full joule with a capital J. So this is wrong, isn't it? But this is right. This is right. Okay. And we don't want to use the other units. Now, what is positive, negative, and zero work? Now we'll come to that thing. Now you see, because you see that this W is equal to Fs cos theta, so any one term of the right hand side, if it becomes 0, your W will be 0. So first we will read about the zero work, when W is going to be 0, and I will give illustrations or examples to you for your understanding. So let me write first W. So W is equal to your net force. Actually this force is your net force. Okay, F S cos phi. This is W is equal to Fs cos phi. Constant for straight line displacement, but still your force is constant. That you must not forget. I am able to write this W is equal to Fs cos theta, W is equal to F dot S. All these are true when the force is constant. Okay. So when the force is constant and straight line displacement, so otherwise there will be misconception. So let me write all these things. So W is equal to Fs. W is equal to Fs cos theta, and W is equal to F dot S. So what are the differences and what are the similarities between all these equations? Let me tell you. W is equal to F dot S and W is equal to Fs cos theta are same. So the first and the third equations are the same thing. The only I have represented by two vectors as F dot S, and F dot S is Fs cos theta. So that is what I have written. Also I can write this as F parallel because F cos theta is parallel. So F parallel S. This I can also write. Now, if I want to, this is all, these are for constant force. So this is the key word is constant force. Conditions are valid so long the force is constant. Okay. Constant straight line displacement. When the displacement and the force are along the same direction, then W is equal to Fs. So this is when both of them, theta for theta is equal to 0 degree. This is theta is equal to 0 degree. But when, suppose this is the body, you are pulling it like this with a force, isn't it? And if this will be S, then which Fs cos, if this is theta, then F parallel or F cos theta into S. Okay. So here force and displacement, here force and displacement are making an angle theta with each other, isn't it? But here they are making theta is equal to 0 degree. But important thing is that this is all valid for constant force. So now coming to W is equal to 0. Look at that. Because on the right hand side there are three terms. What are the terms? F. What is the other term? S. And what is the third term? Cos theta. If any one of them will be 0, then W will be 0. So we'll take from the below. When cos theta is equal to 0, what does it imply? It implies that theta is equal to 90 degree. And what is angle theta? Theta is the angle between force and displacement. So what are the situations? Let us go for a situation. Suppose a person is there, he is carrying a luggage on his head like this, something like a basket full of mangoes, let us assume. Okay. So the weight is acting vertically downwards and he is moving in this direction. So the displacement is along this direction. So this is S and W is the force which is vertically downwards. So this angle is 90 degree. So cos 90 is equal to 0. So the work done by any weight is 0. Because weight and displacement makes an angle 90 degree with each other. So the work done by weight is equal to 0. Similarly, the work done by the normal force is also 0. Because normal force and this displacement makes an angle 90 degree. So cos 90 is equal to 0 and the work done will be 0. So I gave you an example of cos theta is equal to 0 or theta is equal to 90 degree. Then I will give you the second example. When S is equal to 0. Suppose there is a wall of a room, isn't it? And you are pushing that. Suppose this is the room. This is one wall. This is another wall. You are standing here. And you are pushing. This wall is not going to move at all. Whatever amount of force you can push. Okay, not that a machine can push. Even the machine can break these walls. But normally, if you push this wall, because you cannot cause any displacement of the wall, your force is not 0. Theta, cos theta is not 0, but your S is 0. So the work done is 0. So this illustration also I give you. And force, net force is equal to 0. If there are many forces acting on the object, but if the net force finally acting on the object will be 0, then there is nobody to do work for you. So the work will be 0. And on this concept, we will work out and test your understanding. Okay. Before that, let us go for positive and negative work, and then we'll come back to this net force is equal to 0. Why it will produce W is equal to 0. Now, what is positive work? Here your work is positive. When the theta is between 0 to 90 degree, but less than 90 degree. When theta is greater than equal to 0 degree and less than 90 degree, that is an acute angle, work done is positive, isn't it? But when theta is greater than 90 degree, because at 90 degree work done will be 0. So when theta is greater than 90 degree and less than or equal to 180 degree, your work done is negative, isn't it? What is the example of a negative work? If you are lifting a weight from the ground, then the gravitational force or the weight is doing a negative amount of work, because W is vertically downwards. You are lifting the weight vertically upward. So this displacement is in the upward direction. Force is in the downward direction. So force and displacement angle is 180 degree. So F dot S is equal to Fs cos theta. Theta is equal to 180 degree. Cos 180 is equal to -1. So W is equal to minus Fs. So that is an example of negative work. This is an example of positive work. That is an example of negative work. And also I have given you example of zero work. Now we'll work out a test your understanding. 6.1. Okay, what is 6.1? Let us go look at the problem, then we'll go. An electron moves in a straight line towards the east with a constant speed of 8 into 10 to the power 7 meter per second. It has electric, magnetic, and gravitational forces acting on it. During a 1 meter displacement, the total work done on the electron is positive, negative, 0, not enough information given to decide. Can you say the speed is there, the electron is moving, the displacement is also there, it is 1 meter displacement. Now can you say what is the total work done on the electron? Can any one of you say what is the total work done on the electron? Yes, are you able to hear me?
Sir, 0.
Yes, it is 0. Why?
Due to no acceleration.
Yes, you are right. And how do you know that there is no acceleration?
It is written constant speed. 8
Constant
into
speed. Not only constant speed and east direction. That means the direction is also fixed. Straight line towards the east, moving with a constant speed. So the velocity is constant. So there is no acceleration. So there is no force. So there are, though the electric, magnetic, and gravitational forces are acting, but the net forces acting on the electron is 0. So net forces into S cos theta is equal to 0, because sum of all forces is 0. Net forces is 0. That's why no work is done. Good, that is right. Okay, so this is test your understanding 6.1. Now we'll go to, in order to go to the example 6.2. Yes, 6.2, this example we can work it out because it doesn't involve work energy theorem. That just the idea of work is enough, and we have got still 10 minutes. So we can work out that example. Example 6.2. I have written this example 6.2. You can take a screenshot of this example. You can just do it. Are you able to see this question? Yes. A farmer hitches a tractor to a sled loaded with firewood and pulls it a distance of 20 meters along level ground. The total weight of sled and load is 14,700 Newton. The tractor exerts a constant 5,000 Newton force at an angle of 36.9 degree above the horizontal. A 3,500 Newton frictional force opposes this sled's motion. Find the work done by each force acting on the sled and the total work done by all the forces. Have you taken the screenshot of this question? Have you taken the screenshot?
Yes, sir.
Okay. Now we'll work out this question. So example 6.2. Straight away I am drawing the free body diagram. So I am reducing the tractor to a point. Then I am drawing my x-axis, y-axis. Then I will indicate the forces acting on the tractor. One is the slade's weight. Free body diagram for sled. This is FBD for sled. FBD for sled. Okay, this is x-axis. This is y-axis. So this is the weight, which is given 14,700 Newton. Then the tractor is being pulled by a force through a rope. So that's why in the book a T is mentioned. Just for symbol's sake, there is a tensional force, which is 5,000 Newton. But you need not worry about these symbols and all these things. So the tractor is being pulled by a external force whose value is 5,000 Newton. And this angle is 36.9 degree. Okay. So naturally, the perpendicular component or the normal component of the force is useless as far as work is concerned. Only that Fs cos theta will do the work. Then there is a frictional force which opposing the motion of the tractor. That means Fk. Fk is there. It is 3,500 Newton. And there is another force. Another force, which is the normal force. Okay, so this is 1. This is 2. This is 3. This is 4. And the question says we have to find out the work done by individual force and the total work done by all the forces. Okay, so the total work W total is equal to W1 plus W2 plus W3 plus W4. Now tell me, what is the work done by W1? What is the work done by W1? And the displacement is in this direction. This is S is equal to 20 meter. So what is the angle between W and S? What is the angle between W and X?
90.
90 degree. So the work done by the weight will be 0. I have told you earlier. So it is 0. Now, what is the work done by the normal force? Again, you see the normal force and the displacement angle is 90 degree. So W3 is also 0, no contribution. What is the work done by W2 will be FT cos phi. Okay, because phi means cos 36.9 degree. Cos 36 point, this is S actually, 36.9 degree. 36.9 degree. This is cos. Okay, don't take it for phi. FT cos 36 degree, 90 degree into 20 meter, isn't it? So this value. And what will be W4? W4 will be, the force is Fk. Fk cos 180 degree into displacement, that 20 meter. Okay. So if we do the calculation, one will be plus, the other will be minus. So you see what we are going to get. Let us see. So cos 36.9 degree is 0.8. That is 0.8. Its value is 0.8. So 5,000 into 0.8 into 20. 0.8 means 8 by 10 into 20. So this comes out to be 80,000. Okay, this value will be 80,000 joule. 80,000 joule. Similarly, the other part is Fk is 3,500. That is given. Cos 180 is minus 1. So this is minus 1. And distance is 20. So 3,500 into 20 is 7 minus, because minus is there. So minus 70,000 joule. Minus 70,000 joule. So the total is 10,000 joule. So the total work done on this slate is 10,000 joule. So we'll see in the last class what will happen to this total amount of work done. We will guess it, then we will go to the kinetic energy and the work energy theorem. So in this class, we discussed about the test your understanding 5.3. Then I gave you a detailed summary of what are the topics, examples, test your understandings, and the assignment exercises where they are in this chapter 5. And then in chapter 6, there are 4 topics, and we have covered one topic, that is what is work, zero work, positive work, negative work, work done by a constant force, and then when the work is zero, I gave you illustrations, and we did test your understanding 6.1 and an example 6.2. So in the next class, we will discuss from here that what will happen to this slate if it will receive 10,000 joule of work, or 10,000 joule of work is done on a slate. And from there, we'll go to kinetic energy and the work energy theorem. So I think I should stop it here. Okay. So thank you very much for your attention. We'll meet in the next class. Okay, so thank you very much.
Thank you, sir.
Thank you, sir.
Okay. Okay.
Good afternoon, all.